Hello and welcome to Lecture 5 in Equilibrium Chemistry. Today we're going to look at Bronsted Lowry acid-base theory. And it's a long lecture, so I've decided to divide it up into two. Today we're going to look at the overall theory, and in my next lecture we're going to look at predicting Bronsted Lowry acid-base systems. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis for the bulk of diploma exam questions that you'll see. And hopefully you're referring back to this page from time to time to get a sense of how well you're mastering the material. So far in high school, we presented you with two concepts of acids and bases. In grade 10, we introduced you to Arrhenius Theory of acids and bases. An Arrhenius acid was something that donated protons into an aqueous environment. And the classic example was hydrochloric acid. Here we see it ionizing into the hydrogen ion and the chloride ion. An Arrhenius base donated hydroxide ions into aqueous solution. And again, the classic example was sodium hydroxide. It dissociates into the sodium ion and the hydroxide ion. In grade 11, we introduced you to a modified Arrhenius theory, where species reacted with the water to produce either an acidic or a basic environment. So the water was no longer the medium, it was a reactant in the system. By definition then, a modified Arrhenius acid reacts with water to form hydronium. For our purposes, hydronium can be thought as chemically equivalent to a proton. So we see that here. Here our hydrochloric acid is reacting with water to form the hydronium ion and the chloride ion. A modified Arrhenius base reacted with water to produce hydroxide ion. And we'll look at an example of ammonia, which is an interesting example. It reacts with water by stripping a proton off the water to form the ammonium ion, and there's our hydroxide, which generates the basic environment. Modified Arrhenius theory explained why some materials, such as the ammonia, generated acidic or basic environments with no hydroxide or hydrogen in them. However, neither theory could explain acidity or basicity in non-aqueous environments. Nor did either explain how some species can act as an acid in one instance and a base in another instance. An example of this is the case of the sodium hydrogen carbonate, or everyday baking soda. Baking soda forms a basic solution in water. However, it can act as an acid to neutralize a stronger base, such as the sodium hydroxide we just looked at. So, in water, the reaction sequence looks like this. First of all, the baking soda dissociates into the sodium ion and the hydrogen carbonate ion. And then the hydrogen carbonate ion reacts with water by stripping a proton off of it to form hydrogen carbonate and the hydroxide ion, which of course is generating the basic environment. However, when we mix baking soda with a stronger base, such as sodium hydroxide, you see a different series of reactions. Firstly, the sodium hydrogen carbonate dissociates into the sodium ion and the hydrogen carbonate ion. At the same time, the sodium hydroxide dissociates into the sodium ion and hydroxide ion. But then the hydrogen carbonate ion reacts with the stronger base, with the hydroxide ion, to form the carbonate ion and water. So it's removing the hydroxide out of solution and dropping the pH. It's acting as an acid, in fact. We're left to ask, therefore, if baking soda is an acid or a base, and the answer is both. In some instances, it acts as an acid. In other instances, it's a base. And we've seen this before. In the redox system, we saw that a species can be an electron donor or an electron acceptor. Depends on what it was reacted with. The model contemplated a tug-of-war for electrons. So in the case of copper, it spontaneously donates electrons to silver. It reduces the silver. And we see that here in this reaction. On the other hand, copper will spontaneously oxidize zinc. It'll strip electrons off of zinc because it's a stronger oxidizer than zinc. And we see that here in this reaction. Bronsted Lowry theory relies on a similar tug-of-war, except this time it's a tug-of-war for protons rather than electrons. And we have a proton transfer model to explain the dual properties of some compounds, why in some cases they act as acids and donate protons, whereas in other instances they act as bases and they accept protons. By definition, a Bronsted Lowry acid is a proton donor. while the Bronsted Lowry base is a proton acceptor. A Bronsted Lowry reaction equation shows the reaction between the strongest acid and the strongest base in the system. And my next lecture will deal with how to predict a Bronsted Lowry reaction in any given chemical system. We can ignore all other species in the system, which is, again, sort of harkens back to the work we did in the redox system. We do this because at the end of the day, the strongest acid will lose a proton to the strongest base. So therefore, in the reaction between hydrogen chloride and water, the water is acting as the Bronsted Lowry base. It accepts the proton from the hydrogen chloride, which is acting as the Bronsted Lowry acid. And we see that here. The hydrogen chloride is donating a proton to the water to form the hydronium ion and the chloride ion. The hydrogen carbonate ion in the baking soda can be seen to act as an acid in one system and a base in the other. And we call this property amphoteric. The material is said to be amphoteric. So by way of example, the hydrogen carbonate ion reacting with hydroxide is acting as an acid. And we see that here. The hydrogen carbonate ion donates a proton to the hydroxide to form the carbonate ion and water. So it's donating a proton, which is our definition of a Bronsted Lowry acid, and it's neutralizing a stronger base. The hydrogen carbonate ion and hydronium acts as a base, and we see that here. The hydronium ion donates a proton to the hydrogen carbonate ion to form hydrogen carbonate and water. So it's acting as a base by receiving a proton, and it's neutralizing a much stronger acid, the hydronium ion. There's a similar expression called amphiprotic. Amphiprotic is a species that can both accept and donate a proton. And we see that above in the hydrogen carbonate model. In the first instance, it's donating a proton. In the second instance, it's receiving a proton. Hydrogen carbonate's interesting because it can act as both an acid and a base in water at the same time. And we see that here. It'll, in some instances, donate a proton to water, acting as an acid, to form the carbonate ion and hydronium, but it's got a very small Kc, 10 to the minus 11, so it's a very weak Bronsted Lowry acid. But at the same time, it'll act as a Bronsted Lowry base. It'll strip a proton off of water to form hydrogen carbonate and hydroxide, and also a very small Kc, 10 to the minus 8, but 1,000 times bigger than the Kc for the above reaction. And it's this difference that explains why the hydrogen carbonate ion, and indeed baking soda, generates a basic environment in water. And I'm making that comment here. The Kc for the second reaction is much bigger than for the first. Therefore, the hydrogen carbonate ion reacts predominantly as a base in an aqueous environment. We can prove experimentally, if we want to, that the hydrogen carbonate ion is amphoteric by demonstrating it'll neutralize either a strong acid or a strong base. So it'll neutralize a strong acid by way of the following reaction. So here's our hydrogen carbonate ion reacting with hydronium to produce hydrogen carbonate and water. So it's a Bronsted Lowry base. It's receiving a proton from the hydronium ion and thereby neutralizing it. And in a strongly basic solution, it'll act as a Bronsted Lowry acid. It'll donate a proton to the hydroxide ion, which is the strongly basic system, to form the carbonate ion and water, and thereby neutralizing the strong base, the hydroxide. You probably noticed that I've been using double arrows, and I've been describing these reactions with Kc values. Bronsted Lowry acid-base systems are systems in equilibrium. Both the forward and the reverse reactions involve the transfer of a proton. Therefore, both the forward and reverse reactions involve Bronsted Lowry acids and bases. In every Bronsted Lowry system, there's 2 acids and 2 bases. And we see that here. The acids compete to give up a proton, while the bases compete to gain that proton. In the following acetic acid system, the Bronsted Lowry acid for the forward reaction is the acetic acid, while the Bronsted Lowry acid for the reverse reaction is the hydronium. And we see that here. Here's our acetic acid. It reacts with water in the forward reaction by donating a proton to it, and thereby acting as a Bronsted Lowry acid. In the reverse reaction, we see the hydronium ion donates a proton to the acetate ion to reform the acetic acid and water. So our two acids then are the acetic acid in the forward direction and the hydronium ion in the reverse direction. And you'll see that the reaction only proceeds just about 1.3%. So the vast majority of acetic acid exists in water in molecular form, making the hydronium ion a much stronger acid than the acetic acid. Bronsted Lowry theory also defines the relationship between acetic acid and the acetate ion, and hydronium and water. It describes what's known as a conjugate acid-base pair. And by definition, a conjugate acid-base pair differ by a single proton. The acid has the proton, and the base has lost the proton. And we can tabulate these relationships as follows. So the first conjugate acid-base pair is the acetic acid, which is the conjugate acid, and the acetate ion, which is the conjugate base. The second conjugate acid-base pair is the hydronium ion, which has the added proton, and water, which does not. So the hydronium ion is the conjugate acid, and water is the conjugate base. For aqueous hydrogen chloride, also known as hydrochloric acid, and other strongly acidic systems, the water molecule wins the competition for the proton, and it does so overwhelmingly. So it makes the stronger of the two competing bases. And we see that here. Greater than 99.9% of this system exists as hydronium ions and chloride ions. So in the conjugate acid-base pairs are as follows. The hydrochloric acid is the conjugate acid, and the chloride ion is the conjugate base. And you'll see that they differ by a single proton. The second conjugate acid-base pair are the hydronium ion is the acid, and water is the base. And again, they differ by a single proton. The extent to which an acid transfers its proton to water determines its strength as an acid. Strong acids have a very weak grip on their protons, and they easily lose them to any base, even a very weak base such as water. And the general rule in this regard is that a strong conjugate acid will have a very weak conjugate base. And a weak conjugate acid will have a stronger conjugate base. So that's the general theory of Bronsted Lowry acids and bases. I've got a couple of questions, and then I'll refer you to any homework that your teacher assigns in this matter. Which of the following is a Bronsted Lowry conjugate acid-base pair? And again, we should recall that a conjugate acid-base pair differ by a single proton. And so let's look at our four choices. Choice A, the difference between the two species is a sodium ion. So this is not a conjugate acid-base pair. B, the difference between the two particles is two protons. So again, not a conjugate acid-base pair. C, hydronium and hydroxide, well, they differ by two protons, so not a conjugate acid-base pair. D, though, you'll notice the hydrogen carbonate ion and the carbonate ion differ by a single proton. So the answer then is D. That's the Bronsted Lowry conjugate acid-base pair. The strongest Bronsted Lowry acid in the system is, well, Bronsted Lowry acids donate protons to Bronsted Lowry bases. You'll see in the forward direction, the acetic acid is donating a proton to water to form the acetate ion and hydronium ion. In the reverse direction, the hydronium ion is donating a proton to the acetate ion to form water and acetic acid. But the extent of the forward reaction is very low, 1.3%. That means that the hydronium ion is much better, much stronger at donating protons than the acetic acid, making the hydronium ion the strongest Bronsted Lowry acid in the system, and our answer here is D. I hope you found that lecture of value. Next time we'll look at how to predict an overall Bronsted Lowry reaction for any given chemical system. Thank you.